Okay, welcome back. We are now going to continue our study of Shor's algorithm, building it up from, I want to say first principles, but we're not starting from first principles. We're actually starting pretty high. We're starting from a basic understanding of quantum mechanics, and we're starting from the discrete Fourier transform, which we covered in the last lesson. So today we want to talk about the quantum version of the discrete Fourier transform, and we'll now call it the quantum Fourier transform. This is the definition of the discrete Fourier transform in analysis, the forward version. And this is an example of the forward version of the quantum Fourier transform. And it's pretty easy to see that the basic idea here is that this time series data just gets replaced by basis vectors of the underlying Hilbert space of the register. So let's make sure that the terminology is extremely clear on how to interpret this equation. So the first thing we interpret is the J and the K are registers. So they should have a little number there. Now, as I said, Nielsen doesn't drop those numbers in all the time. They assume you understand this point. But that's one of the things that kind of makes this more difficult to read, is you've got to keep track of everything. But by context, we should know that this is a register and J is a decimal number that represents the state of the register. So the decimal number 4 would represent a register in the state 0, 0, let's see, it would be 0, 0, 1, like that. That would be a 4, right? This state is the same as that state, all right? So the idea is we have a decimal number here on the left, J, and K is a decimal number written, and it's the decimal equivalent of a base 5, of a base 2 number with 5 bits that represents the literal state of each qubit, which is just chosen as a basis state for the entire Hilbert space. So now sometimes, well, we won't do that now. So the summation is over from k equals 0 to n minus 1. And a reminder, n is 2 to the L minus 1. So in our case, it would be 2 to the 5th minus 1, which would equal 31. And from starting from 0 to 31, you get 32 states in your register basis. And again, Nielsen does do the L. So I keep saying, oh, we're going to follow Nielsen, and then I show you all these things I'm doing differently. I'm realizing that now. For example, I haven't started quite yet, but I know that at some point in these notes, I do add these subscripts here all the time, which he doesn't. And he always has 2 to the L in my place of n, where I have n here. See, I don't want to write 2 to the L there, right? I think I mentioned that last time. Somebody brought up this very good point that in some references, you will see this e, let's see, what we see? We'll see e to the 2 pi I over n, right? You'll see that completely swept up into a number called omega n, I think. I think they use omega n. They might use omega n J. They might actually absorb the J in there too, right? You can go all the way and absorb the J if you want. But regardless, you'll see this, and that's a really nice typesetting facility, right? It simplifies typesetting a lot. You still have a superscript there. I seem to remember the J as part of the notation. But you can definitely make the, I guess what they'd be called is the roots of unity, right? If you just wrote it like this, and then you would write omega n to the J K, like that. I've seen lots of references do that just to simplify the notation. However, Nielsen never does that, or hasn't done it yet that I've seen. I've kind of read through all the relevant parts of the book. But we're not going to do that. We're going to have to live with the exponentials. What I'll do is I'll eventually stop using e raised to the power, and I'll just write the exponential function in brackets. And that, I think, is the best way to do it myself. Okay. So as I was saying, the summation will always be over all of the states. So the summation is going to be over 0, 0, 0, 0 all the way to 1, 1, 1, 1, 1 on this side. And the basis vector that you're actually transforming, this decimal number j, will land here. So every term of the sum, j is going to be the same. K, however, is going to change, so this phase will change for each of these basis states, and it'll all be normalized by the square root of 1 over 32. And that is basically how this is done. That is the quantum version of the Fourier transform. Now, what we'll do eventually is we will show how this process here is actually the quantum Fourier transform. This is going to be an operator. You know, we could call that operator Q, I guess, and it should have an adjoint, right? And we're going to show that it's unitary. So we'll show that Q adjoint equals 1, right? We're going to show that this process is a unitary process, which any reasonable operator in quantum mechanics almost always is. So that's one of the next steps we're going to do. And the other thing to remember is that the state on the left-hand side, this J state as I've written it, is also a basis state, right? This is the sum of all the basis states, but this is just one basis state. So this represents the transformation of one particular basis state. However, a register doesn't have to sit in a single basis state. A register can be in an arbitrary state in the Hilbert space, and that's represented by the obvious sum of all the basis states in the Hilbert space. So you're summing J now over every basis state. And now x sub j here represents the amplitude. So that's a complex number that represents the amplitude. And this whole thing represents, you could call it the state psi, for example. And the process of the quantum Fourier transform is a linear process. And that is reflected by the fact that this summation here, right? This summation here, whoops, let me draw it correctly. This summation here is just brought right over, and then the transformation on J comes directly from here and gets put right in there. And that's linearity, right? It's just the sum of the transform of the sum is the sum of the transforms. Or this side is we want to do the transform of this sum, but what we're going to do is we're going to sum up the transforms of each of the pieces of the sum. And that's super important, but what's really fun about this is if you look carefully, right, what you see is xj, of course, has to, slot over, but I can swap the two sums. Everything is finite here, right? The basis state is not an infinite Hilbert space, so I can swap it. I don't even think it would be necessarily a problem if it was infinite in this particular circumstance, but regardless, you can swap the sums without any fear of anything going wrong. And then I can not only swap the sums, but I can also take the amplitudes and move it into the sum under J. And then what I have is this object. And that object is exactly the same as this object. In other words, this is the discrete Fourier transform of these amplitudes. So the Fourier transform of an arbitrary state in the register's Hilbert space is simply swapping out the probability amplitudes with their discrete Fourier transforms. So that shows that's the best way of seeing the connection between the quantum Fourier transform and the discrete Fourier transform, because it basically is a discrete Fourier transform. It literally is a discrete Fourier transform on these amplitudes, right? And so if we go back to the condition we were in up here, right? Well, what's this state? This state is, I can list out all of the amplitudes. I can list out x0, x1, ... then there'll be x, let's see, how would that work? yeah, there would be an xj dot dot dot, and then there would be xn minus 1. When I was wondering how it would work, I'm always trying to remember, do we stop at n minus 1, and would this xj actually be the jth amplitude? But yes, if j equals 0, the amplitude is x0. If j equals j, the amplitude is xj. But the point is all of these guys are going to be 0 all the way through xn minus 1, right? All of these will be 0. And this guy will be an amplitude of 1. So you're going to take the discrete Fourier transform of some data that kind of looks like this, right? And we know those zeros, despite the fact that there's zeros in the, we'll call it the time domain, although this I guess would be the amplitude domain, the discrete Fourier transform of these numbers, it's going to spread out and be even. We learned that lesson, right? It's kind of like a delta function in the amplitudes, right? So this is going to be a superposition of all the states, despite the fact you started with 1. And that's a lesson we learned from our discrete Fourier transform stuff. So this formula applies just fine, even if you don't have this sum here, right? If you don't have this sum, you always do have a sum there, right? It's just this string of zeros. And that would have surfaced no matter how you did this, because even if you did it this way, these xj's, right, would kill everything except for one term, which would be this term, and you recover that formula, right? Okay, so that is our introduction. That is our first introduction to the quantum Fourier transform. All right, so now let's do a version by hand. Let's walk through the Fourier transform of a quantum register by hand. So the register we're going to choose is this register right here. We're going to start with, I want to say an easy register, but you'll see that there is a reason to call this the easiest register to compute, but I also want to call it like the ground state of the register. But that language is not generally used in the work I've ever read on theoretical quantum computation. They never refer to this as the ground state of the register, despite the fact that each qubit is in its own ground state, right? Or each qubit is in the ground state. They never worry, for example, in quantum computations, the theoretical form, they never worry about, say, spontaneous emission. And because of that, or spontaneous transitions from the excited state to the ground state of a two-level system, they're always assuming that whatever state you make your register in, it's stable. And, well, I don't even know if they assume that. I mean, to them, this is all just mathematics, right? The idea that this state in the middle of your calculation could suddenly turn into 0, 0, 0, 1, 0, because this bit dropped from 1 to 0. That's not usually part of the algorithmic study of theoretical quantum computation. There is a field called error correction where things like that presumably are relevant, but not in the stuff we're talking about. So using the words like ground state is not typical, is the point of all that. So let's see what we're going to do here. We're going to start with this state. So this state here, this 0, 0 state, that's our j, right? So the value of j equals 0 because 0 in base 2 is 0. And, well, let's see. This base 2 number in base 10 is 0. And that's why j equals 0. Remember, whenever we have this form, the number inside the ket is a base 10 number, right? Okay, so we're going to sum over all 32 basis states. So k is going to get summed over a lot. And this number j, this base 10 number j, is going to land right here inside the exponent, or the argument of the exponent. And so in this case, right, in this case, j is 0. So you're always going to have a 0 there. And so this phase is never going to change. It's always going to be 1 for the entire sum. So this becomes the easiest sum to do. You're summing over all of the basis states, and you get a straight admixture of the states all normalized by 1 over the square root of 32. So this is why I'm saying this is the easiest of the basis states, right? That's why I used the notion of, I called it easy, because it's easy because all these phases end up just going away in that particular case. However, there's nothing special about the basis, the zero state of a register, except for the fact that, see, I'm contradicting myself a little bit. Most algorithms demand that you start your register in this state. And the presumption there, I think, is that when they build a quantum computer someday, no matter how they do it, it's going to be relatively easy to set up that state to start it with. So there is a certain amount of favoritism in these algorithms about that state. So it is special in that sense, is that although they're not thinking mechanically about how to execute these algorithms, they do think in their mind, well, it's probably going to be easier for those engineers to cook up this state to start the algorithm instead of, say, that state. And that may or may not actually be true. It's probably very dependent on the hardware that we ultimately get someday. But let's compare this to the quantum Fourier transform of, say, a different state, say the one state. In this case now, j equals 1. You can tell that I haven't really started to introduce my fives yet. I think I just now, and the light bulb is coming on as I'm typing out the LaTeX, that I should be including these fives, these little fives in there. But so now this j equals 1, right? That decimal value 1 goes right there. And so now the phases do change, and they change by 1/32 every different basis state until you end up with the last basis state, the 31 basis state, and you get a phase of 31 over 32, which is most of a full rotation. So this is just a little rotation, and this is a little more rotation, and a little more rotation. So that one's not too hard to understand either. And then I said, well, let's just look at 20, right? And, it's the same thing, right? This 20 lands right there, right? Replacing the j. The k is being summed over. Again, it's summed over as decimals, right? So this one here, k equals 0, k equals 1, k equals 2, all the way up to k equals 31, and that's 620. Now, what's kind of interesting is, like, this is huge, right? What is that number? It's 620 times 2 divided by 32. That's 38.75. So 38.75. So we're going to break that down, and this is almost a little introduction to our next section. So it's 38 plus 3/4, right? So we're going to have this times pi I, right? So this first part here is an even number times pi I. So that's just 1. So the only relevant part is this 3/4. So the way I've left it is, if you look at this is a lot of rotations. It's well, let's see, I guess it would be 19 rotations and then a little left over, 3/4 of a rotation left over. So, so if you were to try to prepare a state like that, you would have to take a basis vector and give it a phase of 19 full rotations and a little extra, or you could just give it the little extra, right? So we're going to see in a moment how our notation captures this excessive rotation stuff. So we don't have to worry about precisely rotating 19 times and then adding a little more. So we can save the engineers some trouble, right, by getting rid of this part. Now, there is a price to be paid for that, but we'll see that in the next section. Okay, so for this last part of today's lesson, we're going to set ourselves up for the next lesson by understanding yet another piece of sort of notational convention that Nielsen and Chong use that's super important, and it also shows up. It shows up in other places as well, mostly because everybody, I think, uses Nielsen and Chong. But anyway, what you'll notice through this process, this entire process we did, I'm leaving this example of the basis state 20 on the screen, is that although it was fun to have these bits, we never really needed them, right? I could easily have just written 0, 5 here, and 1, 5 there, and I guess 30, 5 there, and 31, 5 there. I never needed to write down these individual bits, right, for these basis states. And the process would have been perfectly fine. However, there is a notational system where you do, in fact, use all of those bits. And we'll see that next time, and we'll see why it's so valuable. But it has a lot to do with eliminating those extra spins, those extra rotations. So how does this notation work? So what I want to introduce is, let's start with our decimal number, j equals 17. That we now know, by now you understand that we would write that state in a 5-bit register, for example. I like 5 bits as my sort of standard example, but of course this is usually written with the capital letter L or the little letter N in different treatments, but we're just going to leave it with 5 just because that's what we've done. So j equals 17, I can write it this way, or I can write it this way, right? And what I'm going to introduce now is the idea that for any value of j, I can break it down into each bit by giving it a subscript. So j1 for 17 is going to be 1, right? This is the value for j1. The most significant bit is j1. Then j2 gets a 0. j3 gets a 0. j4 gets a 0. And in our case for 17, I guess j5 gets a 1. So now we have a way of representing each bit symbolically. So if I just speak of an arbitrary j without assigning it a number, and I want to know what the most significant bit is, I say j1. If I want to know what the least significant bit is, I say j sub l, which in our case is 5. So this is symbolic notation that is important to keep track of. Now, obviously, j itself, the decimal value of j, is given by this simple sort of base 2 expansion, j to the 5th times 1, j sub 5 times 2 to the 0, j sub 4 times 2 to the 1, j sub 3 times 2 squared, j2 times 2 to the 3rd, and j1 times 2 to the 4th. Now, don't get a little this is a little confusing. I mean, it's obvious, but it's a little confusing. The most significant bit for a 5-bit processor is 2 to the 4th. So it's L minus 1 that goes up here, right? L minus 1 is this most significant power. And also just keep track of the lower the number on j, the more significant the bit, okay? These are little things that can kind of crop up and confuse you. But the notation, sorry about moving this around here, but the notation that's important is if I take all of these j values and I string them together like this, I just put them in a line right next to each other. I am not multiplying them out, right? That'd be absurd because there's always going to be some 0 in there, except for the one out of all the states will end up just being 0. But if I string them all out like this, what I mean is this is a representation of the number j in decimal form. So this string of digits is literally this process right here. And in our case, it equals 17, right? So when you see a string of these numbers all lined up together, it's a stand-in for this sum, and it's a stand-in just for the decimal number j. All right, so that's going to become important because you can imagine if I went over here, I could just replace this j with this idea of, let's see, I could write j1, j2, j3, j4, j5. I could put that right in there, And nothing changes about our process, right? Because this number actually equals 20, because this is a single number that's represented by j1 times 2 to the fourth plus j2 times 2 cubed, all the way down to j1 times 2 to the 0, right? Which equals 17, right? So that's important and a touch confusing, I think. But I mean, it's in principle confusing. Hopefully I've explained it so there's no more confusion. Now, there is another key piece to this, whereas if I put this 0 point in front and I string these things up, well, now I'm kind of doing the opposite. I'm taking J1 is still the most significant bit, but now I'm dividing it by 2. J2 is the next significant bit, and I'm dividing it by 4. And likewise, 3 dividing by 8, 4 dividing by 16, and now J5 is actually being divided by 32. So this is the binary decimal form. This is a binary, it's totally like a normal decimal in base 10, but it's a binary decimal. I've never really had to use binary decimals before, but here we are. And so this binary decimal, right, you can also think of it as this thing here, this value. This is just j. Again, I can't stress enough that this guy right here just equals j. So if I take j and multiply it by 1 over 32 to the negative 5, I'm going to move the decimal all the way over. It's going to be 1, 2, 3, 4, 5, just like you would get 1, 2, 3, 4, 5, and the decimal would be here. And I put a big 0 up in front to call your attention to everything, but that 0 is just there to call your attention to the fact that a decimal exists. But likewise, if I took j and multiplied it by 2 to the fourth, I'd get 1, 2, 3, 4. 2 to the third is 1, 2, 3. 2 to the negative second, 1, 2, and 1. So all of these are decimal forms that you can achieve, and you can put decimals right in the middle there, and it just represents j times some inverse power of 2. And then as a warm-up, well, actually, we've already warmed up. Right now, if you look at just these decimal powers of 2, what do you see? Well, everything to the left of the decimal, these are all integers, right? And everything to the right of the decimal, these are all fractions that are less than 1, right? So if we start using this notation in place of our decimal notation that we've been using before, right? In place of our j, right? If we start replacing it with our j1, j2, j3, j4, and j5, notice that we're going to have this n here, which is 2 to the minus 5, right? Well, if we bundle those two together, we're going to end up with a decimal there, right? That whole bundle is going to be, this is going to equal j divided by 2, not 2 to the minus 5, I guess, divided by 2 to the fifth. It'll be equal to j times 2 to the minus 5, which is this decimal form. So now I can get rid of that n and leave j in its decimal form. So we're going to start doing that. We're going to see why this is valuable in our next lesson. Because in our next lesson, what we're going to do is we're going to take this Fourier transform of this quantum Fourier transform, and we're going to give it a completely different representation that is super useful. And in fact, Nielsen says this other representation is really the way we should think of it. It's called the, I don't think he gives it a name, but it's the factored form. So instead of using all the basis states of the register as the basis states, we are going to examine each individual qubit's state, and we're going to take the product of individual qubit states, and we're going to understand how we can understand the quantum Fourier transform in those terms. Okay, so this is hopefully our last stint with having just to deal with pure notational questions, but it's not too hard, right? This is all arithmetic in the end. But these formulations are weird, like looking at a string of symbols all put together and thinking of it as a single base 10 number through this calculation. You got to be used to that, and keeping track of where this decimal is when you move it around is also important too. So you got to keep track of all these things. Okay, so with that, I'm excited for the next lesson where we actually really dig into the quantum Fourier transform's different representation. So I'll see you next time.